right. Good afternoon, everyone. Like Brad said, my name is Sam Green. I'm working at Sandia National Labs, and I'm also a PhD student at UC Santa Barbara. And this talk is a collaboration with Craig Vineyard, who is also at Sandia, and my advisor at UCSB. And in this talk, I'm going to move back over to we're going to swing back over to the machine learning aspect of things. And during the past 3 or 4 years, there's been a lot of work in the computer architecture community building accelerators for deep neural networks. And along with that, there have been a bunch of mathematical optimizations designed to speed up the inference or the forward pass operation for deep neural networks. And, around the same time as we started seeing the impressive DNN results on ImageNet, there was also a spike, or there's been an increasing interest in reinforcement learning, specifically deep reinforcement learning. And we're going to start, we've seen a bunch of interesting applications at this point, and we're going to see people start to design accelerators for DeepRL. And before designing accelerators for DeepRL, it's going to be useful to look at how the mathematical optimizations that are being applied to DNNs affect DeepRL performance. And this work is a preliminary study where we have applied some of the existing mathematical optimizations for DNNs toward RL applications. And RL has been mentioned, I think, by most speakers today, or this week. Perhaps some of the things that haven't been mentioned yet is that some of the results that have applied RL to robotics. There's been some great work out of Berkeley where the researchers trained a robotic arm from end to end to learn how to open doors on its own. And some other good work from Chelsea Finn, where a robot got to basically stir its arm around a bin of parts and learn in an unsupervised way of how to push parts around given certain actions. And it did that by learning how to visualize using recurrent nets. It learned how to predict the effects of its actions. And recently, there's been a paper that I like that came out that was related to task-oriented language grounding by Chatblock. And in this paper, the researchers had a simulated environment where they could tell the robot to, let's say, go find the chair furthest from me and furthest to the right. And it was an end-to-end system that learned how to perform tasks like that in simulation. This is our reinforcement learning environment. We have an agent that exists within an environment, and it gets state observations from the environment. Those state observations, in the context of this talk, will go into a neural network, and the output of the neural network will be a probability distribution, and the agent will take an action on the environment. And the whole point of the action is to induce rewards from the environment. And along with rewards, state observations for the next time step are also emitted from the environment. And in this talk, I'm going to be looking at an old algorithm called vanilla policy gradient. And this algorithm is the basis for all of the algorithms that you see coming out of, DeepMind and OpenAI and other researchers basically have greatly improved this algorithm, but we're using this as a starting point. And the algorithm, or in this case, the policy, is represented by a deep neural network. And we're going to use stochastic gradient ascent to try to maximize something. And what we're trying to maximize is a sum of rewards over all of our time steps. So I'm going to be discussing things from a finite time horizon where capital T is the horizon. And R of tau means, well, R of tau is equal to the sum of rewards. And because RL was initially designed to work in stochastic environments, what we're trying to do is we're trying to maximize our sum of reward, our expected sum of rewards. And so that expectation becomes our objective. And because our policy is represented by a neural network, we can differentiate it, and then we can use stochastic gradient ascent to move the parameters in directions that increase rewards based on previous experiences. And that's called the reinforced algorithm. Here is a toy example where we have a drone trained to collect the boxes in simulation. And in this case, we have a CNN is representing the policy. And for each box that the drone hits, it gets a reward of +1. It gets nothing if it doesn't hit a box, so we have sparse rewards for our states and our actions. And the policy is stochastic, so the input is the image, the output is a state, is a probability vector, and in this case we have 3 possible actions, left, forward, and right. And for this toy example, the probability of selecting left would be 40%. I'm going to be looking at 3 of the optimization methods that are currently being used for DNN inference optimization. I'll be looking at pruning, which reduces the number of neurons or the number of weights in a fully connected layer. We'll be looking at quantization, which lowers the number of bits of precision of any types of parameters, and you can apply quantization to fully connected or convolutional layers. And we'll be looking at weight sharing, which forces weight values to be shared in a single fully connected layer. And I'll cover these details. I'll go over the details for these. Okay, so currently, if you look at the DNN accelerator community's work, all of these chips that are being designed are only designed for forward pass, because to do backpropagation in the way that that community does it is they're using full precision to accumulate all of the gradients. And that's what we're going to be doing here too, is we're just talking about forward pass. And we have a similar motivation when we talk about deep RL optimization. We have a similar motivation as the DNN community, or as in the, here I have the CNN accelerator community, and that's we want more efficiency. And obviously more efficiency doesn't mean lower power. More efficiency just means maximizing whatever your performance metric is. A major difference between a discussion about deep RL acceleration and CNN acceleration is that you may have more sophisticated architectures that you want to accelerate with deep RL. For example, some of the work I mentioned earlier, where the end-to-end robotic grasping and manipulation training is being done, they actually use a recurrent convolutional neural network to visualize the possible outcomes of any given action. And so if you want to use something like that in real time, then you're going to need to have some parallelism involved, where you're visualizing the outcomes of many possible actions. And so I think that there could be some rich architectures in this space. From a power standpoint, I don't really think this community, needs the motivation. But just at a high level, if we compare 32-bit values and 8-bit values across some of the biggest, most popular CNN designs, we can see a pretty dramatic difference. So on the top here, we have some popular CNN architectures. And on the rows, we have various costs. Actually, the first 2 rows show the number of weights and the number of multiply and accumulates needed for each of these networks. Let's look at VGG16, just because it's the largest here. For a single inference, VGG16 has to load 138 million 32-bit values from memory. And for a single inference, we have to perform 15.5 billion multiply and accumulate operations. Now, if we do that at 32-bit precision, or if we do that, let's say, let me just jump to it. If we do that at 8-bit precision versus 32-bit precision, then we're going to use 20 times less power for multiply and accumulate, and 4 times less power there'll be 4 times less power from reading out of DRAM. All right, so now I'm going to get into some of the comparisons that we did. So what we did is we have a full precision neural network that's trained to perform on 3 separate tasks. The neural network has a single hidden layer with 200 units in that hidden layer. And we're going to use a fixed step size for the stochastic gradient ascent. And we're going to apply simple or vanilla policy gradient to 3 OpenAI gym tasks. Specifically, we're going to look at cart pole V0. And the purpose of cart pole is to keep an unactuated arm balanced by moving this cart along this rail. And in this case, we have 4 state observations. We have the cart position, the angle of the pole, the cart velocity, and the rate of change of the angle. So we don't need, because this state observation gives us everything we need in terms of our time, we don't need to keep track of time dynamics. We don't have to use a convolution, we don't have to use an RNN to solve this task because the state observations give us the information that we need. That's just a side note. The output or the action space for this task is +1 and -1 to go left and right. And then the reward is +1 for each time step we can keep the arm balanced. And the episode will end after 200 time steps. Another task is Acrobat, and the purpose of Acrobat is for the agent to swing its arm above the line. And in this case, the only joint that's actuated is the middle joint, and the other joint, the lower joint in the current image, is freely swinging, and it has to swing the lower limb and learn how to swing it so that it can get above the line. And with this task, we have our reward is -1 per time step, and it ends in failure after 500 time steps if it's not successful. Finally, we look at Pong, and I think most of us are familiar with Pong. And in this situation, our state observation is quite a bit different than the other two. It's going to be pixels. And at the end, what happens is both sides, so the left-hand side is so this is running an Atari emulator. The left-hand side is actually the original Atari AI agent. The right-hand side is the learned RL agent. And the game ends when either side gets to 21 points. And then the final score is our score minus the agent's score. However, in this environment, it tells you the reward each time step. So it's sparse again, but if you hit the ball past the agent, you get a 1 at that time step. Okay, so let's look at this is the quantization method that I used. It's called Binary Connect, and it came out 3 years ago. It was one of the earlier DNN optimization methods, and essentially all Binary Connect does is it puts each of the full precision weights through a sine function during the forward pass, and if the full precision weight is positive, it converts it to +1, and otherwise it's a -1. And then from a optimization perspective, what this does is it eliminates the need for multiplication, which, using the estimates that I used earlier, a 32-bit multiplication is approximately 3 picojoules, and we can get to a third of that by just using signed addition. This So just so you know how backpropagation works with some of these algorithms, basically what they do is they perform the optimization during forward pass, and then backward pass, full precision 32-bit floating point is used to accumulate all of the gradients, and the full precision weights are used during training. And after training is finished and you have the performance that you need, you can finally binarize everything and you don't need full precision anymore. Here are the results using binary connect in combination with vanilla policy gradient. These plots, what you're seeing here is the dark blue plots are the full precision, the results from using a full precision policy, so no quantization. And this plot right here are the results for cart pole. And the x-axis, excuse me, I forget that you can't see the mouse cursor. The x-axis are the number of episodes that we run. And basically what happens is that we run an episode, and then we perform stochastic gradient ascent after the episode is over, and then we run another episode. And we do that over and over again. And what you see is that with cart pole, with full precision, we get up to 200 points pretty quickly, so that's the best you can do. And then you see during the next update, or actually the whole way across for the blue plot, you see high variance. And the high variance is a result of two things. One, if you start working with RL, all RL methods have high variance, so this is a problem with reinforcement learning. The second reason you see it here is because we're using an extremely large neural network, too large for this task. A third reason is because of the simplicity of the algorithm. I'm using one of the older RL algorithms. Okay, so now if we look at the orange plot, that is binary connect applied to vanilla policy gradient. And you can see that basically it does nothing. It really never learns anything. Now if you look at the upper right-hand plot, that is a modification of binary connect it's another algorithm called binary net. And with binary net, the activations of the units are also quantized to positive, negative 1, and 1. And so it's actually even more compressed than just compressing the weights. And in this case, you can see that the binary net version actually learns something at around time step 500 or 5,000. And something just to point out is that with all of these methods during training, if you reach a point in training where you have stable performance, you would obviously be doing logging and keeping track of all of your weights. And if you would store the weights if you ever see stable performance. And so then you would have a policy that you could use in the future to solve that problem. Okay, now let's look down at Acrobat and see how binary connect performs. Again, it doesn't perform in this case. It does horribly. Although, just as a note, if you look at the full precision results, you can see that the variance for the exact same architecture is way better for the cart pole, or for the Acrobat task. And that is also an attribute of reinforcement learning, where you can have one algorithm that works well on one task, and it's going to work radically different on another task. However, if we look at binary net, the lower right-hand corner, we see that binary connect at the very beginning achieves some interesting performance on this task. The second optimization method we looked at is pruning. With pruning, what we do is we perform full precision training for n episodes. So basically, we use full precision training until we achieve the performance that we need. And then we eliminate the smallest weights in the network. We just set them to 0. And from there on, we fine-tune the remaining weights. And the benefit of pruning is it reduces the amount of memory and traffic required. So that obviously lowers the cost to run these things and load these things. And it reduces the number of mathematical operations if you have architecture that can take advantage of sparse matrices. Here are the results of pruning applied to cart pole. So you can see that we ran at full precision for 5,000 episodes of the cart pole task, and then we pruned, and then the performance recovered after another 5,000 episodes. The last optimization we looked at is weight sharing, and with weight sharing we also perform with full precision until we achieve adequate performance. And then we use k-means clustering of the weights in each layer, and we lock all of the clustered weights to the same value from that point on, and then we fine-tune the remaining locked weights. And this reduces the amount of memory and traffic that you need in order to load the weights into your accelerator from memory. And here are our results using 8-means clustering. So again, our hidden layer has 200 units, and then each of the environments has a different number of state observations, so that leads to a different number of weights. But whatever number that is, for each of these tasks, after we perform pruning, clustering, we lock them to 8 possible values for each problem. And we can see that in this case, that clustering significantly improved our variance and our performance on the cart pole task, and that's in the orange. And for Acrobat, it also improved things. And also there was a minor improvement in Pong. In Pong, this is the first time you've seen a Pong plot in this talk. The goal is to get to 21. And so you can see this, it has extremely high variance. We get to an agent that can totally beat the opponent, maybe one time at episode about 15,000 or so. And then during the update processes, because of the high variance of the algorithm, it gets bad, and then it performs well again, and so on. Okay, so we also looked at one other method that mixes the optimizations. And on the left, that's a plot you've already seen. That is binary net on Acrobat. And what we did is we performed quantization on the inputs to the hidden layer, and then we allowed the network to have full precision on the output layer. So it's a mix of the method on the left and full precision. And we can see that gives us some interesting performance where we repeatedly achieve policies that have high scores. One of the issues with this early study is that we used a large number of hidden units for these tasks. These control systems tasks don't need anywhere near 200 hidden units to solve. And so we also performed an ablation study. And in this case, HBN is the hybrid method that I just talked about, where the first layer, the weights in the first layer are quantized to be -1 and 1, and the output layer is full precision. And I'm going to show you the results on Acrobat across 6 different architectures. This first architecture on the left has a single hidden layer with 64 hidden units, and the light colors in this case, in this test, I added variance to the plot so you could see the variance. So we could see that the hybrid method didn't perform very well with 64 hidden units. But then when we shrink the network down to 32 hidden units, we can see that the hybrid method outperformed the full precision method. And, as a side note, look at how the full precision method is performing on this task. Even though it's way over parameterized, the full precision method is still able to deal with the over parameterization and learn this task. The reason you'll see why I say that in a moment. Once we have compressed, so now in the upper left-hand corner, we have compressed to 16 hidden units. We can see that the hybrid method outperforms the full precision method. And -1, I should have explained this number better, but -1 is actually means that it took 100 time steps to swing the arm above the threshold. And that's about as good as we see in general, is -100. Now we go down to 8 units on the upper right-hand corner. We see great performance out of the compressed model, and then eventually everything kind of degrades. Okay, so obviously what we're seeing with some of these optimization methods is sometimes we see them performing better than the full precision methods, and that's because that's kind of an artifact of this test in that it's over-parameterized to begin with, and so when we apply these quantization methods, it is applying a form of regularization to the networks. Going forward, because we're interested in energy savings, these small networks aren't that interesting from an energy perspective. They're not doing that much work to begin with. We're now looking at applying these methods at convolutional neural networks and measuring how they perform in visual tasks under these optimization constraints. Thank you.
Thank you, Sam. Any questions? While the next speaker comes up, I have a quick one. So is the reinforcement learning kind of in its structure being, kind of get to the overfitting of these models? I mean, like you say, the models are really large for the size of the problem. Does reinforcement learning kind of expose that? Is that what you think is happening?
Well, excuse me. Okay, so it's interesting to me. Right now, a lot of us we measure our performance when we look at these image data sets. We have a community accepted benchmarking set and then a test set, and those distributions are fixed. With reinforcement learning, your distributions are not fixed. They are a function of both the environment and your policy behavior. And it's speculated that when you have your policy has too high of capacity in RL, you're memorizing your previous experience, and you're trying to perform like you performed in your previous experience, and you're overfitting to your last experience. And then if you reduce the capacity to where it needs to be, then you don't have that problem as much.